What I thought about presenting today is like some of the recent things that I've been doing. So I guess most of you have seen like roaming around the Software Institute between the office and the Sandbox Lab, either running or crashing this small vehicle. So today I thought like I could tell you like a bit more in detail what's the research behind it, what the community is doing, and especially about the main characteristic and peculiarities of the problem that we are trying to solve. So the context concerns these so-called self-driving cars or driverless cars that are expected to be deployed like in public roads in the upcoming years. And this is all premised on their potential to be safer than conventional vehicles driven by humans, ideally. Testing this kind of software is particularly laborious because, so first, human drivers drive camera-equipped cars and record driving data, such as the images experienced like on the road or the driving commands by the human. So all this data is then used to train deep neural networks for behavioral cloning. That means imitating the human driver. Once the model is trained, it is like massively tested on simulation platforms. And when it is deemed as sufficiently tested, let's say, it is then deployed on a real car for what is called in-field testing. So this cycle goes on and on like over and over because like there is always that one situation that is unexpected that must be collected and trained properly. So if you are testing this kind of software, there are many specificities and challenges that you have to solve that we are going to see in this talk quite briefly. And the first one concerns model versus system level testing. So in model level testing, it is quite similar to what like traditional people in machine learning do. So they train a model on some labeled trained data, and then they test the prediction capability of the models on some unseen input data, which is also labeled. And the prediction is then compared with the ground truth value, and usually you get some measure of error. So it is intuitive to understand that this kind of testing is quite fast to do in practice. The biggest cost is actually labeling the data. But despite like being cheap, I mean, you could say, okay, if this is a deep neural network that is supposed to drive, there is no actual driving happening here. And you're correct, because this is perhaps the simplest way to test your network. And also the concept of oracle is quite simple, because we deem a test case to pass only based on numerical error that tells us nothing about the driving capability of the network. So is this 0.02 a low error or a big error if the network was deployed on the car? We don't know actually this information. So despite that, because of the simplicity, so in the community, everybody went like full testing mode, and they tried to propose testing techniques for autonomous driving systems based on model level testing. And across the years, we have seen like a number of papers that try to essentially corrupt the original images, either like with very simplistic transformation from the computer vision domain up to very sophisticated generative adversarial networks. It goes by that any of these techniques basically is able to fool the network, because the image is simply impossible to handle in a way correctly from the network. So I mean, the first here I was reading these papers in which the authors were claiming that they found 10,000 bugs in the software, and that was like a bit surprised. Like either the software sucks or there is something going on. Maybe the results may be inflated. And this was the case because perhaps a more realistic way to test this software is to deploy the network into some sort of system in which you can observe the reaction of the system given the prediction of the network. And this is called system level testing. Here the input is some high level test scenario that describes what the test should do in an abstract way. And this is like the test case is made concrete by either like driving the car in the real world or through some simulation platform that can interpret this scenario and generate like some concrete images that are processed by the network. So here it's more interesting because there is actual driving happening. So you can see the reaction of the entire system given the predictions of the network. It is like definitely like more expensive running this kind of test than model level testing because you have to instrument some sort of simulation platform. And also the notion of oracle becomes more complicated because here, like in a full simulation platform, you should, for instance, take into account safety requirements or like passenger comfortness and this kind of thing. So, I mean, understanding whether a test case passes or fails becomes more complex. Nevertheless, like people have actively working on this kind of testing. For instance, the technique at the top proposes the usage of search-based algorithms united with decision trees to try to discriminate part of the input space that are more likely to expose failures, whereas other people, such as our Vincenzo here and other researchers, are trying to automatically generate concrete test cases in the form of roads that the car is supposed to drive. But another aspect that is quite interesting is like, okay, I have two, level of testing, but how do they compare? And the interesting questions here are essentially two. So you would like to understand whether they expose the same failures, or even better, if you can use the cheap model level testing as a replacement of the expensive system level testing. So people have tried to compare these two guys, and essentially, I mean, to make it really short, they generate like a large number of scenarios, and they evaluate all the scenarios according to the model level oracles and the system level oracles. So at the end, like they do this contingency table to try to understand when the two kind of oracles are in agreement, when they both fail or they both succeed, given specific like test configuration. And by reading this paper, I was quite surprised that the biggest number in the table was number in position N3, which essentially means like when the system failure, when the system oracle fails, when the car is going out of the road, the model level failure is low. It means like it's actually correct. The predictions are correct when the car is going out of the road. How can it be possible? So we try to go deep into the replication package provided by the authors, and we found like some specific, I think, like a potential answer for this specific situation. So suppose like this is a road, the authors have a reference trajectory they were comparing to, and this was essentially like an example of a trajectory by the deep neural network. So essentially, the authors were taking into account the entire scenario, also the part in which the car was actually driving good. So if you sum them up and you average across the entire simulation, I mean, there was low agreement because the part in which the car was driving well, I mean, it was overweighting the part in which the failure was happening. So what we thought about doing is studying the problem by trying to isolate the failing site. And by doing so, we actually found in our own replication of that study a high agreement between the two. So our table, like to make it short, looks like something like that, in which essentially the agreement is quite high usually. So to try to answer the questions, I mean, to expose the same failure, I mean, most cases, yes, if you consider like analogous scenarios, either nominal or say close to the failure. But this, this is not, a very good news anyway, because in essence, like what we demonstrate is that model level testing, can only confirm the failures found during system level testing. So there is no other way around in which we can use model level testing as a replacement, because we cannot generate through an offline mechanism the same images, the same user experience that we had during the simulation. So the bad news is that we need system level testing, which is expensive. The other aspect that is interesting in this domain is that you always bump into this dilemma between virtual versus real world testing. And so, if I were to ask you what is real, what would you say? Essentially, Morpheus, like some time ago, came to the rescue, and he gave his own definition. But if I were like a deep neural network, probably I would interpret his definition in this way. So real is something I can sense, perceive, handle, feature. But let's see like the specific interpretation by the deep neural network about reality. Do you see the word real in there? There is no real. Real is not a thing for deep neural network. So all the deep neural network cares is a feature. So regardless where it comes from. So what people and companies are trying to do essentially is to reuse these real world data gathered in the field to train deep neural networks that are supposed to be tested in a simulation platform. Because in a simulation platform, you can generate like a large set of scenarios. You can safely crash the car with no harm to people or to the environment. But you have probably heard about this sim to real gap, this gap between what the simulators can approximate of their reality. So people have tried to, in our community, have tried also to study this problem. The same authors of the paper that we replicated attempt to answer a very, very ambitious question, which is, can we use the simulators as a replacement of the real world data? And essentially they gave like a positive answer, because in their experiments, essentially the error of the network across the two environments was below 10%, which we can debate whether it is low or high. But anyway, in our own experiments, we haven't found any transferability between the two worlds. Like any deep neural network that we train on a simulation platform doesn't drive well or robustly in the real world, and the other way around. So there is this gap. And this is also confirmed like partially by other people in the community who are trying to understand more about this problem by making surveys with practitioners or roboticists, and essentially all confirm that simulators are useful indeed, but you shouldn't trust them fully, because in field testing, is still not completely taken into account into this simulation platform. And the scenario gets further complicated, because the virtual versus real aspect concerns only the photorealism of the images, but simulators should also try to approximate all the kind of mechanical latencies and stochasticities that can occur in the real world during driving, which occurs when deploying your network on a physical asset. So essentially, you have this tension between your model deployed in the simulator and maybe even fully tested on the simulator, but you have no guarantee that you would have the same results or the same degree of reliability when you deploy it on a real car. So in our group, we are trying to tackle these two problems with two specific techniques. We are trying to understand whether we can lower the gap between sim and real world thanks to neural-based techniques that are able to map images across domains. And as you can probably guess, I mean, we are also trying to understand how large is this gap when considering like virtual versus physical platform. And we have decided to use like a small scale vehicle for this problem. So in the rest of the talk, I will try to, I will present you some of the recent results that we have obtained in this respect. So when like considering the two environments, the first, let's say, kind of questions that we try to answer as the following. So suppose I get a deep neural network architecture and I train it both in the virtual environment and in the real world environment under similar conditions, similar, like comparable training sets in terms of size and distributions, and also in terms of the photorealism. Would the two agents like drive the same? Or suppose like that I expose them to the same unseen conditions or hazards, would they fail the same? So if the answer is negative, probably like there is this gap, but probably more likely we are also able to give it a quantification. So the first attempt was to recreate in a simulation environment the same racing track that we have, the Software Institute, so that we could train these two networks that were able to drive robustly, let's say. But unfortunately, we immediately bumped into one problem, which is in the simulator we're used to use a specific metric to evaluate the lane keeping capability of the model, which is how much the car is deviating from the center of the road. And this is information that comes from free from the simulation environment because it's software, you have the power of God. But unfortunately, in the real physical car, this information is not available. So the way we thought to overcome this problem is to try to estimate this information through visual odometry, which is a technique to estimate a measurement of a sensor given another sensor, which is the camera in this example. So I'll try to go through the reasoning that we made. So the reasoning to estimate this information is as follows. So in the simulator, we can produce and label like hundreds or thousands of images with perfect label. So in theory, we could train a predictor of this metric, but it is unlikely that this predictor would work on the real world images because despite similar, they come from a different distribution. So we would have need like a way to automatically try to map an arbitrarily simulated image into the corresponding one in the real world, which is also likely impossible to do, especially for many images. So what we thought about doing is to fool the network to believe that the image is drawn from the real distribution when it is actually generated automatically by a Neurostime transfer technique. So there exists this kind of generative networks that are able to map images automatically from one distribution to another. And we use that to essentially automatically convert arbitrary simulated images into the corresponding ones in the real world. And the assumptions that we make here is that these two guys, if the translation is accurate enough, should have the same label. So having like the availability of many, let's say what we call pseudo real images, then at this point, we can train a predictor of the metric of interest that is supposed to work also in the real world. So the results confirm that it is possible to achieve a quite accurate translation. This is like a demo video that I always use for presenting stuff. And you can see that, more or less the translation is quite accurate. This is not the best model that we have, but I wanted to reuse the video, my bad. So in terms of predictions, we found that essentially the error was very low in practice, even if here the font size is big, but so at the end of the story, I mean, this sort of visual dominant tool worked, so we proceeded with our study. So in terms of trying to understand whether two models drive the same, we use three metrics. One is the steering angle prediction because it's the main output of the network, clearly. The second one is this lateral position. And the third one is the model uncertainty during driving. And it is interesting because, I mean, we didn't know it at the very beginning, I mean, but all three metrics like concur to get an understanding that you wouldn't have if you skip one of the three. Because in terms of steering angles, what we found is that essentially during many driving simulations, the distributions across domains were found to be the same according to statistical tests. And this can be conceiving because you may think, okay, if the networks like tend to predict the same outcome or less, maybe you don't need to drive at all. You may use offline testing. Also, this sort of, let's say, alignment was expected because of our effort to recreate the scene. But this would be sort of a wrong conclusion a wrong conclusion because when we try to analyze the trajectory of the cars, we found like differences that were, I mean, not only statistically significant different, but also like visibly different because I mean, the car were driving like quite differently, despite the predictions were overall, you know, very similar. So this suggests that offline testing at this point is no longer an option because as you see, like the behavior is quite different. So while trying to understand why this is the case, I mean, we don't have a conclusive answer, but if we look at the model uncertainty, so we always found that the uncertainty of the real world model was higher than the corresponding simulated model. So this essentially means that driving in the real world is more difficult, probably because the processing of the images is harder. I mean, you know, real world images are more difficult in a way to process than the corresponding simulated ones. And also, I mean, there is something that should be taken into account, like the stochasticities, like the mechanical latencies between the prediction and when the prediction is actually applied to the wheels. So all in all, this means that real-world testing cannot really be neglected. It's also quite interesting when we try to understand whether two models like fail the same, because like so far we weren't doing like much testing essentially. So the two models were driving the same across many laps in terms of you know, behavior. So the car was staying in lane despite like some differences in the metrics in the metrics. Yeah. So to actually test them, we try to inject common image corruptions and adversarial examples at runtime during driving. And the results here are quite interesting because so we found that essentially for nearly 60% of the conditions, there was an agreement between the virtual and the physical world, meaning there was the same outcome. So given a test configuration, the two agents failed or the two agents like succeed, which is useful, I guess, to prioritize what kind of test you can avoid in the real world, given that the simulation is already like sufficiently, informative, let's say. But unfortunately, there are like some conditions that are, for some configurations, like the outcome was of the physical platform, which is the one that has the main interest for us, was only observable during real-world physical testing. So we cannot completely, rely on the simulation platform. So I've come to the end of the presentation. So I'll try to recap, say, the main insights here. So if you study like a software of this kind, essentially any cyber physical system, you have to deal with these different dimensions, like model level versus system level is the first. So for as far as the autonomous driving is concerned, unfortunately, model level testing is not an option. And this is the case because the task is time and space dependent. I mean, any prediction is dependent on the predictions before, so you can really simulate that without having a real platform. Unfortunately, system level testing is still very expensive if you want to run any, let's say, comprehensive experiment. So what people are trying to do, and what I guess we're also trying to do, is to use a surrogate model of the simulator. So like some sort of software that is able to predict the outcome of the simulation given the parameters. But again, there is no way to drop that cost yet. It is still a big burden. And for what concerns like simulated and versus real versus virtual versus physical, I mean, there is a gap that everybody's talking about, but in our case, we're able to give it a quantification and also to understand what are the conditions that transfer between the two, which is, let's say, a way to try to reduce the cost of physical world testing, which is quite high, I would say. And concerning the other big aspect that causes the gap, which is the photorealism, I think like the future is definitely this neurostyle transfer using generative network, which is also used at Google, for instance, in which they try to import entire 3D maps into their simulators. So they don't even attempt to use like a more photorealistic simulation. So they go fully generative and they try to reconstruct their reality through this network. So I think this could be a viable option also for testing any system of this kind. And that's it. I've come to the conclusion. So I will be extremely happy to hear your feedback, comments, questions, anything.